Hello there, and welcome. Tonight we are going to travel somewhere extraordinary. We're going to leave, gently and quietly, the familiar weight of this world, the hum of the house, the thoughts still circling from the day, the small persistent concerns that sometimes follow us right up to the edge of sleep. We are going to release all of that, and in its place, we are going to travel outward, slowly, beautifully, into the vast, ancient, astonishing darkness that surrounds us on all sides. Tonight's journey is about space, not the frightening, cold, impossible space of science fiction, but the real thing, which is in some ways even more remarkable. The real thing is older than we can comfortably imagine. The real thing contains galaxies that have never been seen by any living eye. The real thing is, in its own strange way, full of warmth. Not physical warmth, but the warmth that comes from knowing that human beings, creatures who began by huddling around fires and watching the sky in bewildered wonder, eventually figured out how to reach up and touch it. This is a story about that reaching, about the rockets and the telescopes, the astronauts and the mathematicians, the quiet engineers in windowless rooms calculating trajectories to worlds no one had ever visited. It is a story about what we found when we got there, and what those findings revealed about the universe we all share. It is a story about light that took billions of years to reach us, about moons with underground oceans, about the pale blue dot of our home as seen from the edge of the solar system. None of this requires you to stay awake. In fact, the best way to receive it is the way you're receiving it now, lying still, eyes resting, the day behind you, the night gently opening. If you enjoy these gentle journeys through science and wonder, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. Let your shoulders soften now. Let your jaw unclench if it has been holding. Allow your breathing to deepen just slightly, just enough to feel the difference. You're safe. You're still. The stars are waiting. Let's begin. Human beings have looked at the night sky for as long as there have been human beings. This is one of those facts that seems simple until you sit with it for a moment, and then it becomes something else entirely. Before written language, before agriculture, before the wheel or the city or the boat, there were people lying on their backs in the dark, staring upward and wondering. The stars were there for all of it. They watched the first fire, they watched the first burial, that they were burning in their steady ancient way, while the very first human children were being born. The earliest evidence we have of humans tracking the movements of the sky comes from cave paintings and carved bones tens of thousands of years old. There is a carved piece of eagle bone found in France that is believed to be over 30,000 years old, marked with notches that some researchers believe correspond to the phases of the moon. Whether or not that interpretation is exactly right, the carving itself tells us something important. People were paying attention. They were watching the sky cycle through its patterns, and they were recording what they saw in the only medium available to them: stone, bone, the walls of caves. It is a little humbling to realize that our interest in the cosmos is not a modern development, not a product of civilization or education. It is something older than all of that. It may be one of the oldest specifically human impulses we have any record of. Long before anyone needed to know the phases of the moon for farming or navigation, people simply looked and looked and kept looking. The sky, for most of human history, was not something remote or abstract. It was a presence. It moved overhead with a regularity that was, in a world full of uncertainty, deeply reassuring. The sun rose and set, the moon waxed and waned, the stars returned to the same positions year after year, with a faithfulness that no other part of the natural world quite matched. You could lose a harvest to drought. You could lose a season to illness, but you could never lose Orion. He was always there in winter, tilting slowly across the southern sky, the 3 bright stars of his belt as reliable as anything in the known world. This reliability was not just comforting, it was useful in a very practical sense. The first calendars were sky calendars. The first navigational instruments were sky instruments. Farmers watched the stars to know when to plant. Sailors watched the stars to know where they were. The ancient Egyptians aligned their greatest monuments to specific stars. The Polynesians navigated thousands of miles of open ocean, using nothing but the stars, the wind, and the feel of the waves beneath their canoes. The sky was not a mystery to be solved. It was a tool to be used, a map to be read, a clock to be consulted. And yet the wonder never went away. Even as the sky became useful, it remained astonishing. Even the most practically minded ancient astronomer, the one who knew exactly where Sirius would rise and what that meant for the flooding of the Nile, must sometimes have looked up on a clear night and felt that old wordless feeling. The feeling that the sky is enormous and you are small, and that the enormity of the sky is not threatening but somehow comforting, in the same way that the ocean is comforting to some people, vast and indifferent and ancient and beautiful. That feeling has never left us. Thousands of years of science have not explained it away. If anything, science has deepened it, because the more we have learned about what is actually up there, the more extraordinary it turns out to be. The first revolution in our understanding of space came slowly, and it came from simply watching. For most of recorded history, the dominant model of the cosmos placed the Earth at the center of everything. This was not stubbornness or ignorance, it was the natural conclusion of observation. The sun appears to move across the sky. The stars appear to revolve around the Earth each night. Everything appears to orbit us. The model that placed Earth at the center matched what the eye could see, and it was mathematically sophisticated enough to predict the movements of the planets with reasonable accuracy. For over 1,000 years, it was the best theory available. The challenge to this model came in the 16th century from a Polish astronomer named Nicholas Copernicus. Copernicus spent decades performing careful calculations and arrived at a conclusion that was both simple and radical. The motions of the planets could be explained far more elegantly if the Sun, not the Earth, sat at the center of the solar system. The Earth, in Copernicus's model, was just another planet, a moving world, spinning on its axis, orbiting the Sun like Mercury and Venus and Mars. Copernicus published his findings in 1543, the same year he died, as though he had been waiting for just long enough to see his life's work in print. The book he produced was dedicated to the Pope and written in such cautious, technical language that it took some time for the full implications to become clear. But they did become clear, eventually, and when they did, they changed everything. What is remarkable about the Copernican revolution, looking back, is not just the astronomical insight, it is the shift in the human sense of place that it required. Before Copernicus, it had seemed self-evident that humanity occupied a special position in the cosmos, the center, the point around which everything else turned. After Copernicus, that specialness became a question rather than an assumption. If the Earth was just one planet among several, what did that mean about the creatures who lived on it? Generations of astronomers and philosophers would wrestle with that question. They're still wrestling with it. But the wrestling has been, in its strange way, productive. The universe that emerged from abandoning our central position turned out to be far larger and more interesting than the one we had been imagining. Galileo Galilei pointed a telescope at the sky in 1609 and the universe has never looked quite the same since. Galileo did not invent the telescope, but he was among the first to turn it systematically toward the heavens, and what he saw was staggering. He saw mountains on the moon, real mountains, with peaks and shadows not so different from mountains on Earth. He saw 4 small moons orbiting Jupiter, which was direct and undeniable evidence that not everything in the cosmos orbited the Earth. He saw that the Milky Way, which to the naked eye appeared as a soft, continuous band of light, was actually composed of countless individual stars, packed so closely together that they merged into that gentle luminous smear. Each of these discoveries was a kind of quiet earthquake. The moon with its mountains suggested that the heavenly bodies were not perfect crystalline spheres, as ancient philosophy had maintained, but real, physical places, subject to the same geological forces that shaped the Earth. The moons of Jupiter suggested that the solar system was more complex and more dynamic than anyone had imagined. The stars of the Milky Way suggested that the universe was larger, far, far larger than the models of the time had room for. Galileo paid a price for his discoveries. He was tried by the Inquisition for his support of the Copernican system and spent the last years of his life under house arrest. But he kept working. There is a story, probably apocryphal but so perfectly suited to the man that it survives regardless, that when forced to recant his belief that the earth moved around the sun, he muttered under his breath, "And yet it moves." The earth, that is. Still moving, regardless of what the authorities required him to say. The discoveries Galileo made with his small, imperfect, hand-ground lenses were the beginning of a process that has continued unbroken for 400 years. The process of looking more carefully, with better instruments, and finding that the universe contains more than we had imagined. Every time we have built a bigger telescope or pointed a more sensitive detector at the sky, we have found something we did not expect. Allow yourself to rest here for a moment. There is no urgency in any of this. These stars have been burning for billions of years, and they will go on burning long after tonight. The discoveries we are moving through have already been made. They are settled, safe, stored in libraries and databases in the minds of astronomers around the world. You don't need to hold on to any of it. Let the information wash over you the way water washes over a stone gently, without force, leaving behind only a faint impression of something large and beautiful. If your eyes have closed, let them stay closed. If your breathing has begun to slow, let it slow a little more. You're exactly where you need to be. Let us continue. Isaac Newton gave us the mathematics that explains why the planets move the way they do. Newton was born in 1643, the same year Galileo died, which has always seemed to some people like a meaningful kind of passing of the torch, though of course it is the sort of coincidence that the universe produces without any particular intention. Newton was a deeply strange man, secretive and intensely private, capable of working on a single problem for years without telling anyone what he was doing. He spent as much of his intellectual energy on alchemy and biblical prophecy as he did on physics. And yet, what he produced in the realm of physics was so precise, so powerful, so elegantly expressed in the language of mathematics, that it remained the best description of how the physical world works for over 200 years. The story most people know is the apple. Newton, sitting in a garden, sees an apple fall and has the insight that leads to his theory of gravity. The story is almost certainly simplified. Newton himself told a version of it in old age, and it has been elaborated upon ever since. But the kernel of truth in it is real. Newton was thinking about falling objects, and he made a conceptual leap that no one had made before. The force that pulled the apple downward toward the Earth was the same force that held the moon in its orbit. Not similar, the same invisible pull operating across the same mathematical rules, binding apples and moons and planets and stars. Newton's law of universal gravitation states that every object in the universe attracts every other object, with a force proportional to their masses and inversely proportional to the square of the distance between them. In plain language, everything pulls on everything else, always. The pull weakens with distance double the distance, and the pull drops to a quarter of what it was, but it never goes to zero. The Earth is pulling on you right now, of course, as you lie still and feel the pleasant weight of that, but you're also, in an almost inconceivably tiny way, pulling back on the Earth, and both of you are pulling, even more inconceivably, on the moon, and the sun is pulling on all of us, across the 150 million kilometers of space between us. What makes this beautiful, beyond the elegance of the mathematics, is the universality of it. Newton's laws were not laws for Earth, or for the solar system, or for the visible sky. They were laws for the universe. The same equations that describe the orbit of the moon describe the orbit of every planet around every star that has ever existed. Gravity does not have local rules and universal rules. It just has rules, and they apply everywhere, always, without exception. This was a genuinely new idea, that the universe was governed by consistent, discoverable, mathematical laws. It sounds obvious now, but it was not obvious then. The sky had been, for most of human history, the domain of gods and spirits and unpredictable powers. Newton made it into physics. He made it, in a deep sense, understandable, and in doing so, he made it eventually reachable. The solar system is older than the mind can comfortably hold. It formed approximately 4.5 billion years ago, from a vast cloud of gas and dust drifting through what was then a younger, quieter region of the Milky Way galaxy. Something perhaps the shock wave from a nearby exploding star caused this cloud to begin collapsing inward, slowly at first, then faster, as gravity drew material toward center. The center grew dense and hot. Eventually it grew hot enough that hydrogen atoms began fusing together into helium, releasing enormous amounts of energy. Star was born, our star, the one we call the Sun. Around that newborn star, the remaining material, dust and ice and rocky fragments, and small molecules of water and carbon compounds swirled in a flattened disk. Over tens of millions of years, this material clumped together through a process that is, in its way, rather beautiful. Small particles stuck to each other, and those clumps attracted more particles and grew into pebbles, and pebbles grew into rocks, and rocks grew into boulders, and eventually the boulders grew into planetesimals. Objects large enough for their own gravity to begin pulling in surrounding material. In time, these became planets. The Earth formed in this way, aggregating from the disk of debris around the young sun, growing slowly over millions of years into the world we know. The early Earth was nothing like the world we inhabit now. It was molten, bombarded constantly by incoming meteors and asteroids, its surface a roiling ocean of liquid rock. There was no ocean yet, no atmosphere in any form we would recognize, no land, no sky in any meaningful sense, just heat and rock and the constant rain of debris falling from the space around it. And yet even in those first violent hundreds of millions of years, something extraordinary was happening. The raw materials of life were already present. Carbon, nitrogen, hydrogen, oxygen, the elements that would eventually combine, in ways still not fully understood, into the first living molecules were all there in the early Earth's mix. They had been there in the original cloud of gas and dust. They are in fact some of the most common elements in the universe. The universe is, in a sense, very well stocked for life. Whether life arises wherever those ingredients are present, or whether it requires some additional conditions we have not yet identified, is one of the great open questions of our time. For now, it is enough to notice that we're here on a world that formed from stardust, around a star that formed from an ancient cloud, in a galaxy that has been turning slowly for billions of years. The atoms in your body and your bones and your blood and the very cells of the brain that is now drifting towards sleep were forged in stars that lived and died before the sun was born. You are, in the most literal possible sense, made of the universe. Not a visitor to it, not an observer of it, part of it. The moon is Earth's closest companion, and it has shaped us in ways that most of us never think about. The moon formed, according to the most widely accepted scientific model, approximately 4.5 billion years ago, not long after the Earth itself. The scenario that most planetary scientists favour goes like this. A young planet roughly the size of Mars collided with the early Earth in a tremendous impact, not a head-on collision, but a glancing blow at an oblique angle. The impact was violent enough to melt and vaporize much of both bodies. The debris from this collision, a vast cloud of superheated rock vapor, spread into orbit around the surviving Earth, and over time that debris coalesced under the influence of gravity into the moon. This is a violent origin story for something that seems so calm and serene in the night sky. But there it is. The moon is, in essence, a fragment of both the early Earth and its impactor, shaped by one of the most dramatic events in our planet's history. Since then, the moon has been quietly, steadily, enormously influential in the development of life on Earth. It stabilizes the tilt of the Earth's axis. This matters more than it might seem. Without the moon's gravitational stabilizing influence, the Earth's axial tilt would wobble chaotically over millions of years, swinging between extremes that would produce catastrophic changes in climate. The relatively stable tilt we have around 23.5 degrees is one of the reasons Earth's climate has been, on geological timescales, consistent enough for life to evolve in a sustained and complex way. The moon also drives the tides. This too is something easy to take for granted, but it has had profound effects on the history of life. Tidal zones, the regions along coastlines that are alternately submerged and exposed as the tides rise and fall, are among the most biologically productive environments on Earth. Many biologists believe that the tidal zone played an important role in the transition of life from sea to land, providing a kind of intermediate environment where organisms could begin adapting to conditions outside the water. And then there is the simple human fact of the moon's light. For most of human history, the moon was the primary source of artificial illumination. Farmers worked by moonlight during harvests. Travellers navigated by moonlight. Lovers met by moonlight. The phases of the moon structured the calendar. The full moon and the new moon marked the rhythm of months, and that rhythm echoed through culture after culture, civilization after civilization, down to the present day when we still use words derived from the Latin word for moon lunar to describe things associated with monthly cycles. On a clear night, the moon is close enough to show detail to the naked eye. You can see, if you look carefully, the dark patches that ancient astronomers called seas Maria in Latin. They're not seas, of course. They're ancient lava plains, the solidified remnants of enormous volcanic eruptions that occurred billions of years ago. but they form patterns that human beings have always found meaning in. The man in the moon, the rabbit, the woman. Different cultures see different figures in those dark planes, but almost every culture has seen something which suggests how deeply the moon has pressed itself into the human imagination. There is something worth pausing to consider in the sheer diversity of what different cultures have found in the same sky. The constellations we learn in Western culture, Orion, the Big Dipper, Cassiopeia, are arrangements that the ancient Greeks systematized, though the stories behind them are older still. But these groupings are not universal. The stars do not naturally divide themselves into the shapes that Westerners see. Chinese astronomers, over their own long tradition of sky watching, divided the same sky into completely different groupings, associated with completely different stories. Indigenous peoples around the world have their own traditions, some of them extraordinarily sophisticated, that describe the sky in ways that bear no resemblance to the Greek system. What this tells us is that the human impulse to find pattern and story in the sky is universal, even if the specific patterns and stories vary widely. We cannot help making meaning from what we see overhead. The stars are just stars, spheres of plasma, generating light through nuclear fusion, but they look from here like a map of something, and maps invite interpretation. Maps invite stories. Maps invite the question, what is this a map of? Over the centuries, different cultures have answered that question differently. For many indigenous traditions, the sky is a mirror of the living world, the stars are animals, rivers, ancestors, spirits. For the Greek tradition, the sky is a myth archive, a place where the stories of gods and heroes are written in light so large that they can be seen from anywhere on Earth. For modern astronomy, the sky is an archive of a different kind, a record of the physical history of the universe, written in wavelengths of light and the signatures of elements. All of these ways of reading the sky are, in their own ways, appropriate. The sky contains multitudes. It always has. Mars has been the planet of human imagination for thousands of years. Even to the naked eye, Mars is distinctive. It glows with a reddish colour that sets it apart from the other planets, a deep orange red that ancient observers associated with blood and fire and war. The Babylonians called it Nergal, the god of plague and death. The Greeks called it Ares, the god of war. The Romans kept the association and called it Mars, the name we still use. Every culture that noticed it attached some version of the same meaning. This is a dangerous, martial, powerful thing. The colour comes from iron oxide rust that covers much of the Martian surface. Mars is, in a sense, a rusted planet. It was not always this way. Evidence gathered by rovers and orbiters over the past several decades suggests that Mars was once a much more Earth-like world. It had liquid water on its surface. It had a thicker atmosphere. It may even, in its earliest period, have had conditions suitable for some forms of life. What happened to Mars is a cautionary tale written in geology. The planet lost its magnetic field, probably because its interior cooled more quickly than Earth's, and the dynamo that generates a magnetic field, the churning of liquid metal in a planet's core, slowed and stopped. Without the magnetic field, the solar wind, a constant stream of charged particles flowing out from the sun, began stripping away the atmosphere. Without the atmosphere, the liquid water evaporated or froze. Over hundreds of millions of years, Mars went from a world with rivers and clouds and perhaps even rain to the cold, dry, apparently lifeless desert we see today. This transition is one of the reasons Mars is so scientifically fascinating. It may represent a kind of road not taken a world that had the ingredients for life but lost them. Or perhaps it is more complicated than that. Perhaps life began on Mars and found ways to persist in protected niches deep underground, where liquid water may still exist. We don't know. The rovers we have sent to Mars have found evidence of ancient river valleys and lake beds, and they have found organic molecules, the building blocks of life in the Martian soil. But they have not found life itself. The search continues. The first spacecraft to reach Mars successfully was Mariner 4, which flew by the planet in 1965 and sent back 21 grainy images that mark the first time human beings had seen another planet up close, from space. Those images were modest by any later standard, but the scientists who received them and the public who saw them were transfixed. Here was another world, a real one. Not a point of reddish light in the sky, but a surface with craters and clouds and features you could study and map. Mars was no longer just a myth. It was a place. In the decades since, we have sent dozens of missions to Mars flybys, orbiters, landers, and rovers. We have mapped its surface in extraordinary detail. We know its highest mountain is Olympus Mons, a shield volcano so immense that it is roughly the size of France and rises to nearly 3 times the height of Mount Everest. We know its longest canyon is Valles Marineris, a system of canyons that stretches nearly a quarter of the way around the planet, dwarfing the Grand Canyon in every dimension. We have found evidence of seasonal frost, ancient river deltas, vast deposits of ice, and a sky that occasionally turns pink from dust storms that can engulf the entire planet for months at a time. Let your breathing slow just a little more now. You've travelled a long way tonight, from the first human eyes studying the sky by firelight to the great volcanoes of Mars. There is no need to hold on to any of the details. Let them settle into the background like the sounds of a gentle rain or the breath of someone sleeping nearby. The universe is large enough that you will not run out of it. There is always more, and it will be here when you want it. If your body is feeling heavy, let it be heavy. Let the bed hold you. Let the night hold you. You're doing exactly the right thing. From here, the story shifts outward, beyond the red planet, into the realm of the giants. Jupiter is the largest planet in the solar system, and its scale is difficult to truly take in. If you wanted to fill Jupiter's volume with Earth-sized spheres, you would need more than 1,300 of them. Jupiter is so massive that all the other planets in the solar system combined could fit inside it, with room to spare. It is so large that it generates its own heat, not from nuclear fusion as the Sun does, but from the slow gravitational compression of its own interior, still radiating the warmth of its formation billions of years ago. In some ways, Jupiter is almost a failed star, a world that had the right ingredients, but not quite enough mass to ignite. Jupiter has no solid surface. It is composed primarily of hydrogen and helium, and as you descend into its atmosphere, the pressure increases until the hydrogen transitions gradually from gas to liquid to something strange and exotic, metallic hydrogen, a state of matter that does not exist anywhere on Earth under ordinary conditions, in which hydrogen is squeezed so tightly that its electrons move freely the way they do in a metal, making it electrically conductive. Deep inside Jupiter, this ocean of metallic hydrogen generates the planet's enormous magnetic field, one of the most powerful in the solar system. What we can see of Jupiter from the outside is its cloud tops, which are organized into dramatic bands of different colors, pale creams and tans and whites, interspersed with darker brown and orange bands. These bands are the tops of enormous atmospheric circulation systems, jet streams moving at hundreds of kilometers per hour, some flowing east and some flowing west. The different colors arise from different chemical compounds, various sulfur compounds, ammonia crystals, phosphine that react with sunlight in different ways. The most iconic feature of Jupiter's visible atmosphere is the Great Red Spot, an enormous storm, roughly the width of 2 Earths, that has been continuously observed for at least 3.5 centuries. It is the largest known storm in the solar system, a swirling anticyclone that has been turning in the same direction for as long as humans have had telescopes capable of seeing it. The Great Red Spot has been shrinking over the past century. It was larger in the 19th century than it is now, but it shows no signs of disappearing. Like so many things about Jupiter, it operates on timescales that make human experience seem brief and local. Jupiter has at least 95 known moons, a number that grows as our instruments improve. Most of these are small, irregular objects captured by Jupiter's immense gravity over billions of years. But 4 of them are substantial worlds in their own right, and they were the ones Galileo observed in 1610. He called them the Medicean stars, in honor of his patrons. We call them the Galilean moons, Io, Europa, Ganymede, and Callisto. Europa may be the most compelling world in the solar system for those who wonder about life beyond Earth. Europa is roughly the size of Earth's moon, and from a distance it looks unusual. Its surface is bright white and strikingly smooth, crisscrossed by long curving lines that look, in some images, like the cracks in the surface of a hard-boiled egg that has been gently squeezed. Those cracks are exactly what they appear to be, fractures in a sheet of ice that covers the entire moon. Beneath that ice, according to the best current evidence, lies a liquid water ocean. Not a small pocket of water, but a global ocean potentially twice the volume of all the Earth's oceans, combined, kept liquid not by the warmth of the sun, which is so distant that it provides very little heat at Jupiter's orbit, but by a process called tidal flexing. Europa orbits Jupiter in an elliptical orbit, and as it does, Jupiter's immense gravitational pull squeezes and stretches the moon slightly, like kneading bread dough. This constant flexing generates heat in the moon's interior, and that heat keeps the subsurface ocean liquid. The ocean of Europa is thought to be in contact with a rocky seafloor, which is significant. On Earth, the places where the deepest oceans meet the seafloor in certain tectonically active regions host communities of extraordinary organisms. Creatures that live not on sunlight, but on chemical energy released by hydrothermal vents. These ecosystems function in complete darkness, fed not by photosynthesis, but by chemosynthesis. If similar hydrothermal venting occurs at the bottom of Europa's ocean, and there are reasons to think it might, then Europa could, in principle, host life. This is one of the most remarkable possibilities in contemporary astronomy, that within our own solar system, orbiting the same sun that warms us, there is a world with an ocean, and perhaps something living in it. We have not been there yet. The spacecraft we have sent to the Jovian system have given us tantalizing hints but not answers. But missions are planned. Europa Clipper, launched in 2024, is currently making its way toward Jupiter to conduct detailed observations of the moon. In the coming decades, we may know whether we are alone in the solar system. That is an extraordinary thing to be able to say. Saturn is, by most measures, the most immediately beautiful thing in the solar system. Even in a modest amateur telescope, the kind of instrument you can buy for a few $100s and set up in a backyard, Saturn's rings are visible, and the sight of them stops people cold. Time after time, at public astronomy events and science museum demonstrations, people lean into a telescope eyepiece expecting to see a white dot, and instead see a perfect, tiny, golden orb encircled by a luminous band, tilted at an angle that makes it look almost like an ornament, almost too perfect to be real. And the response is almost always the same, an involuntary noise, a sharp intake of breath, and then a long silence. The rings are composed of billions upon billions of individual pieces of ice and rock, ranging in size from tiny frost particles to chunks the size of houses. They extend outward from Saturn's equator for hundreds of thousands of kilometers, but they're astonishingly thin in most places, only about 10 to 20 meters thick. If you scaled Saturn down to the size of a basketball, the rings would be thinner than a sheet of paper. The rings are not a permanent feature. Astronomers believe they formed relatively recently, in geological terms perhaps only a few 100 million years ago, possibly from a moon or a comet that strayed too close to Saturn and was torn apart by the planet's tidal forces, and they will not last forever. The inner edge of the ring system is slowly being drawn inward by Saturn's gravity, and ring material is raining down into Saturn's atmosphere in a process that, at current rates, would deplete the rings entirely in perhaps 100 million years. We exist at a particular moment in solar system history when the rings are young and bright and magnificent, and we have managed to notice them. In that sense, we are lucky. Saturn's moon Titan deserves its own moment of quiet attention. Titan is larger than the planet Mercury. It is the only moon in the solar system with a dense atmosphere, a thick, orange haze of nitrogen and methane that shrouds its surface from view in visible light. Beneath that haze, revealed to us first by the Cassini spacecraft and the Huygens probe it carried, is a world of extraordinary strangeness. Titan has lakes and seas, not of water, the surface is far too cold for that, but of liquid methane and ethane. The same chemical compounds that we use as natural gas on Earth exist on Titan in liquid form, pooling in enormous lakes near the poles, evaporating and forming clouds and falling as rain, flowing in rivers that carve channels into the landscape. It is a hydrological cycle exactly like Earth's water cycle in its mechanics, but made of hydrocarbons instead of water. Titan may be the most Earth-like world in the solar system in terms of having complex surface processes driven by a liquid cycle. It is also, in a different sense, profoundly alien. To stand on Titan's surface would be to stand in dim orange light. The sun, from Titan's distance, is about 100 times less bright than it appears from Earth in a cold far beyond anything in human experience, surrounded by an atmosphere you couldn't breathe but that was thick enough to walk through without a pressurized suit. It would be strange and somehow beautiful in the way that all deeply alien things are beautiful. Uranus and Neptune are distant cousins, a pair of ice giants that we have barely had a chance to meet. They share a similar composition mixtures of water, ammonia and methane ice surrounding rocky cores, with gaseous envelopes of hydrogen and helium and similar colours, a pale blue-green caused by the methane in their atmospheres absorbing red light and reflecting blue. But they have distinctly different personalities. Uranus is tilted, dramatically, almost absurdly tilted. Its axis of rotation lies nearly on its side, nearly 98 degrees from vertical, compared to Earth's 23 degrees. This means that Uranus orbits the Sun essentially rolling on its side, with its poles alternately pointing toward the Sun. The most likely explanation is a catastrophic collision early in the solar system's history, with a body perhaps as large as Earth, that knocked Uranus onto its side and left it there. The result is the most extreme seasonal cycles of any planet. Each pole experiences roughly 42 years of continuous sunlight, followed by 42 years of continuous darkness. Neptune, though farther from the Sun, is curiously warmer than Uranus. It generates more internal heat. It also has the most violent wind speeds in the solar system, with gusts reaching over 2,000 kilometers per hour. At the time of the Voyager 2 flyby in 1989, the only spacecraft ever to visit Neptune, astronomers observed a feature they called the Great Dark Spot, a large storm system reminiscent of Jupiter's Great Red Spot. But Neptune's spots are more ephemeral. By the time the Hubble Space Telescope turned its gaze toward Neptune a few years later, the Great Dark Spot had vanished, replaced by different atmospheric features. Neptune's clouds come and go on timescales that we can actually observe, which makes it somehow feel more dynamic, more changeable, more alive than the more stable giant planets closer to the Sun. Neptune was discovered in a way that demonstrates the extraordinary power of mathematics. By the mid-19th century, astronomers had noticed that the orbit of Uranus didn't quite match what Newton's equations predicted. There was a slight discrepancy, a wobble, that suggested the presence of some unknown body whose gravity was tugging on Uranus. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated where this unknown planet should be, based purely on the disturbances it was causing. Their calculations pointed to almost exactly the same location in the sky. When astronomers turned a telescope to that location in September 1846, there was Neptune, within 1 degree of where mathematics had predicted it would be. This was one of the most dramatic demonstrations in scientific history, that the universe follows mathematical laws, that the behavior of matter, even in the depths of the solar system, could be predicted from equations worked out in a study on Earth. Newton, who died more than a century before Neptune was discovered, had laid the groundwork for its discovery. Mathematics reached out across billions of kilometers and pointed to a planet no one had ever seen. It is worth pausing here for a moment to notice something about where we are in this journey. We have moved outward from the Earth, past Mars and Jupiter and Saturn and Uranus, to Neptune, the 8th planet, orbiting at an average distance of about 4.5 billion kilometers from the Sun. And we have still, by cosmic standards, gone almost nowhere. Neptune's distance from the Sun, expressed in the scale of the universe, is comparable to taking one step across a football field. We haven't even reached the edge of the field. Beyond Neptune lies the Kuiper Belt, a vast region populated by small icy bodies, including the world once called the 9th planet, Pluto, which was reclassified as a dwarf planet in 2006, to the dismay of many people who'd grown attached to it. Beyond the Kuiper Belt lies the Oort cloud, a vast, diffuse sphere of icy bodies extending perhaps a quarter of the way to the nearest star, barely bound to the Sun by its distant gravity. This is where comets originate. They fall inward from the Oort cloud, triggered by gravitational disturbances, swinging through the inner solar system on orbits that take thousands or even millions of years to complete. And beyond the Oort cloud lies interstellar space, the space between the stars, a darkness so profound and so vast that the distances involved require a new unit of measurement, the light year, the distance light travels in 1 year, which is approximately 9.5 trillion kilometers. The nearest star to our Sun, Proxima Centauri, is about 4.25 light years away. The fastest spacecraft ever launched by humanity, Voyager 1, has been travelling for over 45 years and has covered less than 1/5 of a single light year. At that speed, it would take approximately 75,000 years to reach Proxima Centauri. These numbers are difficult to hold in the mind. They are meant to be difficult. The universe is not scaled to human comprehension. It is scaled to itself, and it is very large. Let yourself rest in that largeness for a moment. There is something in the sheer scale of things that invites sleep if you let it. The universe is so vast, and your worries are so specific, so local, so tied to this particular moment on this particular world that, held up against the background of 4.5 billion years and billions of galaxies, they become not unimportant, but small in a comforting way. Small the way your own bedroom feels small and familiar when you come home from a long trip. There is comfort in smallness sometimes. There is comfort in being nested inside something enormous and old and entirely indifferent. Let your body settle into the bed. Let the thoughts that are still circling the unfinished business, the things you meant to do, the words you're not sure you said right, let them drift, the way clouds drift in a sky too vast to hold them. They will still be there tomorrow. Tonight you are here, in the dark, and the stars are burning. Let us continue. The first human-made object to reach space was a small Soviet satellite called Sputnik. It launched on October 4th, 1957, from a launch site in the Kazakh steppe, and it weighed less than 100 kilograms. It was a polished metal sphere, about the size of a beach ball, with 4 long antennae trailing behind it. It carried no cameras, no scientific instruments of consequence, just a radio transmitter that beeped. And that beep, received by radio operators and amateur enthusiasts around the world, changed everything. The beep was heard in the United States with something close to panic. The Cold War was at its height. The United States and the Soviet Union were locked in a competition for technological and military supremacy, and the Soviets had just demonstrated unmistakably, in a way anyone with a radio receiver could verify, that they had a rocket powerful enough to place an object in orbit. That same rocket, it was quickly understood, could carry a nuclear warhead to any point on Earth. But beneath the geopolitical anxiety there was something else, something harder to quantify: genuine wonder. People across the world went outside on clear nights to watch the tiny point of light move steadily across the sky. It was bright enough to see with the naked eye, though many people may have actually been watching the spent rocket casing rather than the satellite itself, and the experience of seeing it was unlike anything that had come before, a human artifact moving silently through space. The word artificial had always been something of a diminishment. Artificial things were lesser than natural things, but an artificial satellite was something new, a made thing, orbiting a natural world. The boundary between the human and the cosmic had shifted. Sputnik's beep lasted only 3 weeks before its batteries died. The satellite itself burned up in Earth's atmosphere less than 3 months after launch, but its effect on human history was lasting and immediate. The space age had begun. Yuri Gagarin became the first human being in space on April 12, 1961. He was 27 years old. He was a fighter pilot, son of a carpenter and a dairy worker, raised in a small village in Russia. He had a wide, open, easy smile. Photographs from before the flight show a young man who seems genuinely happy, genuinely at ease in the way that some people are. He had been selected from a group of 20 potential cosmonauts through a process that evaluated not only physical fitness and piloting skill, but psychological stability, communication ability, and the ability to remain calm under extreme stress. The spacecraft he flew, Vostok 1, was essentially a metal sphere with a small service module attached. It had limited controls for the pilot. The spacecraft was designed to be flown automatically, with manual controls available only as a backup. The flight lasted 1 hour and 48 minutes. Gagarin completed one orbit of the Earth, travelling at roughly 27,000 kilometers per hour, and then re-entered the atmosphere and parachuted separately from the spacecraft. The system wasn't designed to land the capsule with the cosmonaut inside, so Gagarin ejected and descended under his own parachute to a field in the Saratov region, where he reportedly asked a somewhat surprised farm woman and her young granddaughter for the use of their telephone. What Gagarin saw during those 108 minutes has been described many times. He saw the curve of the Earth, the thin blue line of the atmosphere, the darkness of space. He said that the Earth was beautiful. He said, "The Earth is blue. How wonderful. It is amazing." The words have been translated in various ways from the Russian, but the essence is always the same: a young man looking at his home from outside for the first time, struck by its beauty and fragility and colour. The philosophical impact of that view of seeing the whole Earth from space has resonated in human culture ever since. Astronauts who have had the experience consistently report that it is transformative. They come home different, or at least they describe something that changed in their understanding of what the Earth is and what we owe it. The experience has been given a name: the overview effect. It is the shift in perspective that comes from seeing the Earth as a whole, not divided by borders or politics or culture, but singular, finite, beautiful, and entirely surrounded by the dark. The Apollo program represents one of the most audacious achievements in human history. On May 25, 1961, President John F. Kennedy stood before Congress and declared that the United States should commit itself to landing a man on the moon before the end of the decade. The goal was partly political. The space race with the Soviet Union was a high-stakes contest for technological prestige and Cold War advantage. But it was also something larger. It was a statement of what human beings were capable of, a deliberate choice to attempt the impossible and see what happened. At the time Kennedy made this declaration, the United States had approximately 15 minutes of total human spaceflight experience. The first American in space, Alan Shepard, had made a brief suborbital flight less than a month before. No American had yet orbited the Earth. The technology required to reach the moon, the enormous rockets, the life support systems, the guidance computers, the spacesuits, the lunar landing craft did not yet exist in any final form. Kennedy was committing to a goal that no one had any certainty could be achieved, on a timeline that required solving an enormous number of problems, many of them problems that had never been solved before, in less than 8 years. What followed was one of the largest organized technical endeavors in human history. At its peak, the Apollo program employed more than 400,000 people. Engineers who had grown up building airplanes found themselves designing spacecraft. Computer scientists who had spent their careers on early room-sized machines had to figure out how to build computers small enough to fly in a capsule, reliable enough to trust with human lives, and fast enough to perform the calculations required for a lunar landing in real time. Women mathematicians, many of them African American, whose stories were largely unknown until recent decades, performed the hand calculations that verified the trajectories and the orbital mechanics that made the missions possible. The guidance computer that flew on the Apollo spacecraft had a processing speed and memory capacity that would seem laughably primitive today. A modern smartphone is, by most measures, thousands of times more powerful, and yet that computer guided human beings to the surface of another world. Neil Armstrong stepped onto the surface of the moon on July 20th, 1969. He was a careful, quiet, precise man. He had been a naval aviator and a test pilot before becoming an astronaut, and he had the test pilot's habit of saying exactly what he meant and no more. He had been chosen to be the first to step onto the moon partly because of his skill and experience, and partly because of his temperament, the sense that he would not be overwhelmed by the moment, that he would perform his tasks calmly and correctly, even in a situation no human being had ever faced before. The words he spoke as he stepped off the ladder of the lunar module, "That's one small step for man, one giant leap for mankind," were slightly garbled in transmission. He later said he intended to say "one small step for a man," the A being critical to the meaning. But in the form in which they were received, and in the form in which they have been remembered, they capture something real. The contrast between the smallness of one individual foot on one piece of ground and the enormousness of what that step represented the arrival of life from one world onto another for the first time in history. Armstrong and his fellow astronaut Buzz Aldrin spent 2 hours and 31 minutes on the surface of the moon before returning to the lunar module. In that time, they collected rock and soil samples, deployed scientific instruments, planted an American flag, and received a telephone call from President Nixon, who was in the Oval Office in Washington, 250,000 miles away. The contrast is almost too much to take in the ancient stillness of the lunar surface, which had not changed significantly in hundreds of millions of years, and the President of the United States on the telephone. The rocks they brought back were among the most analysed pieces of material in scientific history. Lunar samples have been examined and re-examined by scientists for decades, and they continue to yield information. They confirm that the moon was formed from material related to the early Earth, the giant impact hypothesis. They revealed details of the bombardment history of the inner solar system. They told us about the age of surfaces on other worlds. What Armstrong and Aldrin picked up from the floor of the Sea of Tranquility was not just moon rock, it was data, the raw material of understanding. The universe is not only vast in space, it is vast in time. This is perhaps the most difficult thing to truly take in about the cosmos, not the distances, which are at least conceptually understandable as very large numbers, but the depths of time. The universe is approximately 13.5 billion years old. This number is so large that every analogy for it involves other large numbers, which is not especially helpful. But let us try. If you compressed all of cosmic time into a single calendar year, 1 year representing the entire history of the universe from the Big Bang to this moment, then the Big Bang would be at the stroke of midnight on January 1st. The first stars would appear in January. The Milky Way galaxy would form in March. The solar system would form in early September. Life on Earth would appear in late September. The first complex multicellular animals would emerge in mid-December. The first dinosaurs would appear around December 25th. The entire history of human civilization, all of it, from the first cities to the present moment, would take place in the final 11 seconds of December 31st. We are very new. Our most ancient ruins, our oldest stories, our deepest cultural memories, all of these fall within a span of time so brief compared to the age of the universe that on a cosmic calendar they would be difficult to distinguish from the present moment. And yet, in those 11 seconds, or to speak without metaphor, in those few tens of thousands of years we have managed to look up at the sky and figure out what it is. We have deduced the existence of planets we cannot see from the wobble they cause in the stars they orbit. We have detected gravitational waves, ripples in the fabric of space-time itself, produced by the collision of black holes a billion light-years away. We have sent spacecraft to the farthest reaches of the solar system and received photographs from a distance of 20 billion kilometers. We have looked back in time to see light from some of the first stars, light that travelled for nearly 13 billion years before landing on our detectors. This is, in the truest possible sense, extraordinary. Not ordinary extraordinary, genuinely, deeply extraordinary. We are children of the universe, newborn in cosmic terms, and we have managed to see almost all of it. The Hubble Space Telescope has changed what it means to look at the sky. Hubble launched in 1990 with a flaw. Its primary mirror had been ground to the wrong shape, by an error of just over 2 micrometers, less than the width of a human hair. The images it returned were blurrier than expected, and the disappointment was acute. But in 1993, astronauts aboard the space shuttle installed corrective optics, essentially glasses for the telescope, and Hubble's vision sharpened to something extraordinary. One of the most famous images Hubble produced is known as the Hubble Deep Field. In 1995, astronomers pointed Hubble at a tiny, apparently blank patch of sky near the handle of the Big Dipper, a region about 1/30th the apparent diameter of the full moon, a speck of darkness that seemed to contain almost nothing. They held the exposure for 10 days. What emerged was one of the most profound images in the history of astronomy. Not darkness, but light. Thousands of galaxies, each containing hundreds of billions of stars, each at distances ranging from a few 100 million to more than 12 billion light-years away. Galaxies in every orientation. Spirals seen face-on, spirals seen edge-on, ellipticals, irregulars, colliding galaxies already in the process of merging. In every direction we look, in even the most apparently empty patch of sky, the universe is full of galaxies. There are, by current estimates, somewhere between 200 billion and 2 trillion galaxies in the observable universe. The Milky Way, our home galaxy, contains somewhere between 100 billion and 400 billion stars. If there are 2 trillion galaxies, and if each of them has an average of 100 billion stars, then the total number of stars in the observable universe is approximately 200 sextillion, 2, followed by 23 zeros. The number is essentially meaningless to human intuition, but it is what the data suggest. And each of those stars may have planets. We have known since the 1990s that planets are common. The first planet confirmed to orbit a sun-like star other than our own was discovered in 1995. Since then, the count of known exoplanets, planets orbiting other stars, has grown to the thousands, and statistical analyses of the data suggest that most stars have at least one planet, and many have several. The Milky Way alone may contain hundreds of billions of planets. Many of them may be in the habitable zones of their stars at the right distance to have liquid water on their surfaces. We have already found some. Kepler's planet hunting mission changed our sense of how full the galaxy might be. The Kepler Space Telescope, launched in 2009, was designed to do one thing: stare at a patch of sky and look for the tiny regular dips in starlight that occur when a planet passes in front of its star from our line of sight. It is a beautifully elegant method called the transit method, and Kepler executed it with extraordinary sensitivity. Over nearly 10 years of operation, Kepler confirmed more than 2,600 exoplanets and identified thousands more candidates. It found planets of every imaginable type. gas giants as large as Jupiter or larger, rocky worlds smaller than Earth, worlds in the habitable zones of their stars, worlds with orbital periods of a few hours, worlds in binary star systems orbiting 2 suns at once. It found a world where a year lasts less than a single Earth day. It found systems where multiple planets orbit in a configuration so tightly packed that, if our solar system were arranged the same way, all of them would fit inside Mercury's orbit. Among the most intriguing of Kepler's findings were the super-Earth planets larger than Earth, but smaller than Neptune, with no equivalent in our own solar system. We don't have a super-Earth here. We went from the small rocky planets Mercury, Venus, Earth, Mars directly to the gas giants. But around other stars, super-Earths appear to be some of the most common type of planet in the galaxy. We don't know yet whether they are rocky, like scaled-up versions of Earth, or whether they are ocean worlds drowned under global seas or something else entirely. But they exist in enormous numbers, and many of them orbit their stars in the habitable zone. The sheer diversity of planetary systems we have found has been humbling in the best possible way. Before we could detect other planets, it was tempting to assume that our solar system was typical, that other systems would look roughly like ours. They don't. There are systems architecturally so different from our own that, had we first discovered them, we might have built entirely different models of how planets fall. The universe does not constrain its creativity. There is a calculation first formulated by astronomer Frank Drake in 1961 that tries to estimate the number of civilizations in the Milky Way galaxy with whom we might be able to communicate. The Drake equation, as it is known, takes into account the rate of star formation, the fraction of stars with planets, the fraction of those planets that could support life, the fraction where life actually develops, the fraction where intelligent life develops, the fraction where that intelligence produces detectable technology, and the length of time such civilizations might remain detectable. Multiply these factors together, and you get an estimate. The thing is, there is enormous uncertainty in almost every term of the equation. We know something about the first few star formation rates, and the prevalence of planets are fairly well understood now, but the fraction of planets where life develops, we have one data point: Earth. We don't know if life arose here because it almost inevitably arises wherever conditions are right, or because it required an extraordinarily unlikely chain of events. Both positions have thoughtful advocates among scientists, and the truth is we genuinely don't know. Drake himself, running the equation with his best estimates in 1961, arrived at a number somewhere in the tens of thousands of civilizations currently active in the Milky Way. Other scientists have run it with more pessimistic assumptions and arrived at one us, alone or nearly alone, and others have run it with very optimistic assumptions about the ease with which life and intelligence arise, and arrived at numbers in the millions. What the Drake equation captures, even if it cannot be solved precisely, is the depth of our uncertainty and the significance of what we don't know. If the pessimistic answers are correct, and we're alone or nearly so, then the existence of life on Earth is an almost miraculously unlikely event, and we bear a responsibility to that fragile uniqueness. If the optimistic answers are correct, and the galaxy is full of civilizations, then the silence of the sky, the fact that we have not yet received any undeniable signal from another intelligence, is itself a mystery that needs explaining. This is called the Fermi paradox. Given how likely intelligence seems to be and how old the galaxy is, where is everyone? There is no answer to the Fermi paradox that has achieved broad acceptance. There are many proposed solutions. Other civilizations are out there but too far away for their signals to have reached us yet. Other civilizations exist but have no interest in communicating with us. The emergence of intelligence is far rarer than we hope, and we really are alone. Or some danger or transition tends to end technological civilizations before they become capable of interstellar communication. Each of these possibilities carries its own weight of implication. None of them is comfortable. All of them are interesting. Allow your eyes to rest fully now. We have come a long way tonight from the earliest human eyes studying the stars, through the solar system and its worlds of ice and storms and underground oceans, to the billions of galaxies that Hubble revealed in a single blank patch of sky, to the question that may be the deepest question humanity has ever asked: are we alone? There is nothing to resolve tonight. These questions have occupied the greatest minds of every generation, and they will occupy future minds with tools and insights we cannot imagine. Your mind does not need to solve them. Let them simply be questions large, open, full of possibility, drifting in the darkness above you like stars. Let your breathing go its own way now. Let your body feel how it feels to be completely still. The universe is still too, in its way, impossibly active, and yet, from here, impossibly calm. Let us drift a little further. Black holes are among the strangest objects in the universe, and they exist in a realm where the physics we know best begins to break down. A black hole forms when a massive object becomes so dense that not even light can escape its gravitational pull. The boundary beyond which escape is impossible is called the event horizon, an apt name, because it is literally a horizon beyond which nothing, not even information, can return to tell us what lies beyond. If you crossed the event horizon of a black hole, you would not survive, but you would not immediately notice the moment of crossing there is no wall, no visible barrier. You would simply find yourself on a one-way path toward the center, unable to reverse course by any means available to physics. At the center of a black hole, according to the mathematics of general relativity, Einstein's theory of gravity, which replaced and extended Newton's, lies a singularity, a point of infinite density where the equations of physics break down entirely and give results that don't make physical sense. This is widely understood to mean not that a true infinity exists at the center of black holes, but that our current understanding of physics is incomplete. The singularity is where general relativity, our best theory of gravity at large scales, comes into conflict with quantum mechanics, our best theory of physics at tiny scales. Resolving this conflict, developing a theory that successfully unifies gravity and quantum mechanics, is considered by many physicists to be the deepest unsolved problem in science. There are different types of black holes. Stellar mass black holes form from the collapse of very massive stars at the end of their lives. When a star roughly 20 or more times the mass of our Sun runs out of fuel, it can no longer support itself against its own gravity. The core collapses in less than a second, triggering an enormous explosion, a supernova that blows away the outer layers of the star. What remains at the center, if the star was massive enough, is a black hole. Supermassive black holes are something else entirely. They inhabit the centers of virtually all large galaxies, including our own. The supermassive black hole at the center of the Milky Way is called Sagittarius A star, and it is approximately 4 million times the mass of our Sun. The supermassive black hole at the center of the galaxy M87, which was the subject of the first ever image of a black hole in 2019, is approximately 6.5 billion times the mass of our Sun, a number so large that the entire orbit of Pluto around our Sun would fit comfortably within its event horizon. How supermassive black holes grew to be so massive is still an active area of research. They were present at very early times in the universe. There are quasars, objects powered by the accretion of material onto supermassive black holes, visible from when the universe was less than 1 billion years old. How a black hole reaches a mass of billions of solar masses in less than 1 billion years is not fully understood, and several competing theories are being investigated. Gravitational waves gave us a new way of listening to the universe. You've been here long enough tonight. You can go now. Sleep well, and good night.